Alright, hello and welcome back to the proof slides. Let's keep on trucking. Well, let's go back to where we were. So really the goal of this is to take the kind of stuff that we were learning about in the logic chapter and all the proving stuff that we were doing there and make it English rather than a bunch of tables and boxes. This is really the kinds of proofs that math people like to do. We have the tables in the back of our minds, but it's a bit more clean looking to do it by writing sentences and proving your stuff. Okay, it's still correct. So let's talk about proving a for all. Let's say that somebody gives you I don't know, for all x p of x, and it's your job to prove it true. Okay, so if you have a statement that looks like this, starts with a for all, you have a few options to prove it. The easiest one is called proof by exhaustion. Hopefully you'll notice, or you'll know to do it when you see it like this. But oops, what happened? Everything went away. Okay, I think everything's fine. So to prove a statement that's where there's a for all and your domain is small, you can use proof by exhaustion, because if alright, you got to prove p of x is true for all x, and x, the domain of x is between, I don't know, 2 and 5. Just try all of those. Try p of 2, try p of 3, try p of 4, try p of 5. Just make sure they all work, and you have a for all, right? So that's easy. That's proof by exhaustion. Let's see here. And then the harder way is universal generalization. That's the generic way of proving a for all. That's the way that you normally have to do when you have an infinite domain or a very large one. You just prove that your statement, everything after the for all, is true for an arbitrary element. So you're doing what we learned in the logic chapter. You're just doing it in English, all right? So to prove a for all is true, you assume you have an arbitrary element of your domain. Let's say, call it A. Assume A, your element, is arbitrary. It's an element of the domain of the predicate you're trying to use in your for all is arbitrary. It's an element of P, arbitrary, P's domain. And then you go and you say, all right, you prove that P is true. Your predicate is true on A, having assumed nothing about what A was. So it could have been, A could have stood in for any element of your domain. After that, after you do both of those things, you have then proven, therefore, that for all values of A, P of A is true, because you kept A arbitrary. It could have been filled in with any element of P's domain. And if you prove that P of A is true without assuming anything special about A, then it could have worked for any A. Okay, so that's universal generalization. So that's the standard way of doing it if you have a large domain. And then the flip side is much, much easier, because if you have a for all and you're just trying to prove that it's not true, you're trying to prove that a for all is false, then what you do is you just find one good element. You find a counterexample. All right, because think of it this way: if you're trying to show this, you're trying to show that it's not true that for all x, p of x is true. That just means that there's one where it doesn't work, right? You remember that that's equivalent to, you remember how to push it inside, that negation inside, it flips to a there exists. That means there must exist some x such that the negation of p on x is true, right? So in words, that's all right, if you're trying to prove that for all x, p of x is false, then there must be one element, call it maybe e or something, such that not p of e is true, or that p of e is false, right? Because then you found your one counter example, that's what we call it, that shows that it's not true for everybody. There's one element, at least one, that doesn't work out. It ruins the show, ruins the party, everybody goes home. Okay, so that is much easier. You just got to find one good element of the domain if you're trying to prove a for all false. That's called a counter example. All right, and before I get to Englishy looking proofs, I know I've given you maybe a couple. I just want to talk to you a little bit about how people like to make these proofs. It's English, they're writing sentences, but there is a setup. There's a strategy. There's a way that people like to write stuff. So one custom is that you start a proof by just saying proof in all bold with a period. I don't know, mathematicians, maybe they're not really big on surprises. So you know that everything after that is the start of you proving something, or the book proving something to you, right? And then after you're done proving something, it's also customary to just shout out and say, heck yeah, I proved the thing that I was trying to prove. And it's you're essentially including in your proof the mathematical equivalent, I swear to you, it's the mathematical equivalent of a mic drop. So that's when you put a rectangle at the end of your proof. that is a mic drop, essentially. It's saying that I just did that. I proved my proof, and it's done. Alternatively, back in the day, people used to put QED, which is a Latin phrase, but more people nowadays are using the rectangle. But QED is what the rectangle stands for. It's Latin for quod erat demonstrandum, I guess, is how you say it. And that means which was to be demonstrated. So it's like half a sentence. It really is filling in for this idea. Like, I just proved exactly what I was trying to demonstrate or prove. And so that's legitimately, you have a mic drop at the end of all your proofs, which I think is really cute. And so you might as well do it. Just like pat yourself on the back each time. Isn't that fun? So, okay. Here's a question for you. I want you to try proof by exhaustion, because there's a for all. Just try out every element of the domain, because it's easy and it's small. But I'm going to help you. We're going to do this in two parts, all right? Maybe try both, but if you have any, if you want a hint, maybe stay listening. But all right, here's our idea. For every integer n, I would like to show that, for every integer n such that n is between 0 and 3, strictly including 0 and not including 3, show that this is true. All right, that's your proof statement. All right, for every integer n between that range, this better be true about n. Okay, so that is your proof. And then I would like you to try that with proof by exhaustion. And then also, the first thing I want you to do is convert the statement to math. So try doing both, and then I'll do them both for you. Okay, but I think it's easier to start with math, and then we'll look at the domain. Okay, so what is this in math form? For every integer n, that just screams for all, right? You see that it is a for all n, such that n is between, in this range, this must be true about n. Do you see how it's kind of like an if-then? For every integer n, if this is true about n, then I'm trying to show this. I only care when this is true for n, right? Only if this is true do I want to show this, okay? So do you see how that becomes an implication? For all n, if n is between 0 and 3, or 0 and 2, really, assuming that they're just like whole numbers only, integers only, right? For every integer n. If this is true about n, then we're trying to show that this is true also. Then n plus 1 squared is greater than n cubed. See that? So that's your statement. And also, this is your predicate. Do you see it? This is a predicate. This is something about n. It can be filled in with any n, p of n, let's say. See that? So for all n, p of n, that's what we're trying to prove. All right? See how I'm breaking it down like that? And so now to prove it, we're going to use a proof by exhaustion. And usually when you're making a proof, you say proof, period. And then what you do is you start your proof. Also on the first line, a lot of the time, you just try to say to the person how you're going to prove this thing. By exhaustion is how we're going to prove it, so that, you know, mathematicians, they don't like surprises. They're going to understand better what we're trying to do when we say this, by exhaustion. And so what we need to do is we need to show that p of n is true where n is 0, 1, and 2. See that? So what we need to do is we need to show, I'll do this, I'll abbreviate this as NTS. We need to show that p of 0 is true, p of 1 is true, and p of 2 is true. All right? If I've done all of these, right, I've shown it for every one I care about, right? And that means the whole thing is true. Okay, so let's just write it out. So p of 0 is true because what, all right, so 0 plus 1 is 1 squared. 1 squared, is that greater than 0 cubed? So that's, first of all, this side's equal to 1. That is greater than 0 cubed, which is still equal to 0, right? So that checks out, all right? Well, p of 1, you just got to show them all. P of 1 is true because, let's see, 1 plus 1, so 2 squared equals 4. That better be greater than 1 cubed, which is just 1. Yep, checks out. And then p of 2 better be true because 2 plus 1 is 3, 3 squared, which is 9. That should be greater than 2 cubed, which is 8. Yeah, and that all works. So I've tried them all. Do you see how that's proven this statement? You see that works out. So that's the proof. And once you're done, like you've done everything you needed to do, you do your mic drop. You have a little rectangle and you fill it in. Bam, done. Okay, so that's our first proof. Do you kind of see how it's working? Like we're saying proof by exhaustion. We figured out what we need to show to make it so that like we've proven the thing, and then we show those things, and then we're done. That's pretty much it. All right, so that's a proof by exhaustion. All right. So now let's do a harder one. Here's a question for you. I really highly encourage you to try this yourself. That's how you learn how to do proofs. All right. Find a counterexample to the statement to prove that it's false. All right. So this is a statement that is apparently not true, and so I want you to try converting it to math first. That would help, and then show that there's a counterexample. Show that it's not always true. All right. All right. If n is an integer and n squared is divisible by 4, then n is divisible by 4. So do you see how there is an implicit for all going on in here? So for all n, like if this is true about n and this is true about n, then we can conclude this thing. So there's also an if then up in there. So for every n, if this stuff is true, if n is an integer and n squared is divisible by 4, so another way to write that is 4 divides n squared. So if both of those things are true, then if that stuff, then n is divisible by 4, or 4 divides n. Okay, so that's how we'd write it in math. And again, this would be our predicate, so Pn, right, like that. Okay, so that's my P of n for all n, all that stuff, which I can slap into a predicate. Okay, so did you find the counterexample? You just need one value for n where this predicate fails, where it's false. So let's see if we can find it. So what do we got? If you just try a couple, you'll notice that 2 is the one that doesn't work. I hope that made enough sense. You just try it out and, this one fails, okay? This is the answer, and then we have to explain why. Okay, why is it false there? Okay, so first of all, well, it's an integer. It's an integer. So that's important. We need to uphold both of these things, right? The only way, this is an implication, right? We need to make it a false. The only way to make a false implication is to have true imply false. That's the only piece that is equivalent to falsehood. So I need to have all this stuff being true, that and needs to be true, and then this conclusion needs to be false. Okay? So it's an integer, so I have that, check. I also need this to be true. Does 4 divide n squared? Does 4 divide n squared? Yeah, it sure does, because n squared is 2 squared, which is equal to 4. 4 divides 4, surely, because what does it mean for something to divide something? Let's go back to our definitions. Well, we've got something dividing something else if there's some k for which that second thing is equal to a multiple of the first thing, an integer times the first number. Okay? X divides y if there's some k such that y is equal to k times x. So if we scroll back down here, this is working out because 4 is equal to, totally, it's equal to sum to 4, right? It's equal to 1 times 4. Does that make sense? And this could be your k. That's oh, sorry. Excuse me. It's equal to, there's your k, 1 times 4. Did I do it in the right order? Yeah, k times x. Cool. So that's kind of me following the definition there. And so that checks out. So I have true over here. The and makes true for the hypothesis. Then I need to show that false. I have false in the conclusion. So is it true that 4 divides n? No, this is false. So I can say that 4 does not divide n. Write a little slash like that to mean not divide, just like you can write a slash to mean not equal to. 4 does not divide n. This conclusion is false because what is n but 2, right? N is equal to 2. There's no way. There's no way to make 2 from 4, right? 2 is not equal to k times 4. This is my best equal sign, sorry. 2 is not equal to k times 4 for any k. That's an integer at least. It needs to be an integer for it to be divisible, right? For any int k. And that's gonna prove it to us. Okay? 2 is this looks like a z, sorry. So 2 is not equal to k times 4 for any integer k. That's what it means. That's what it would have to have been in order to get 4 dividing n. But no, it's not happening. All right, it's too smaller. You'd have to be like, k would have to be 1/2, right? And that's not an integer. So it doesn't check out. And so we had true over here, false over here. So that means the predicate, the inner part here, is false, and it was supposed to always be true, right? This is supposed to be claiming that it's always true for any n. No. So there's our counterexample, and we've proven exactly why it doesn't work. If you'd like, you could put a little mic drop symbol here, but that's what you got to do. So that's that example. So that's for all. I'll have some more examples of using the generalization. We need to practice some more, though, to get there. Let's also talk about proving a there exists, right? So if you're trying to prove a statement that has a there exists at the start, you just need to find one good element for which it works, right? To find that conclusion being true, okay? And there's a couple ways to do it. Like, all right, first of all, your statement looks like this. Like, it's there exists an x such that p of x is true for that thing. You can either give the value, give the thing for which it works, just explicitly. Like, all right, 2 works, done. Or you can show in a roundabout way that there must be at least one value that works. That is sometimes the case that you have to do it this way. It's very vague, I know. I'll show you eventually an example of, like, you can't come up with the actual number, but you can show that it must exist, all right? So usually people give the value explicitly, all right? So that's that one. This second way, this implicit way, is just like, all right, is something like this. Like, you know, like you've discovered, like, you have some value. A is in the domain. Or even the explicit one. Like, you find some value, some good value A. A is in the domain. Or just prove that it exists. Domain. And then you just prove that P of A is true for it. And you see how that's just shown that there exists some value, so let's call it x this time, such that P of x is true. Because you've just proven that P of A is true for 1A in the domain, well, there exists somebody for which it works. Cool. All right, so that's that one. That's how there exists. It's pretty easy to prove it true. To disprove an existential, it's hard. Just like disproving for all was easy because it turns into a there exists. So if you have a there exists and you negate it, remember it turns into a for all. So that's disgusting. So like if you're trying to do this, you're trying to prove that it's not true that there exists an x such that P of x is true. Well, it kind of sucks because, well, you push that negation inwards and suddenly now you got what? For all x, you got to show that it's not true. Which makes sense, right? If you're trying to disprove this, you're trying to show that there exists x and x such that P of x is true is false, that means that, all right, you try P for every element, right? Every element E of that domain better be false. There's no good one that ever works out, right? Suddenly that turns into a for all for the reason we just showed, okay? So that's proving there exists. And now I have some more questions. Please try this yourself. So prove this. Assume that the domain of these variables involved are integers. Show that there exists an n1 and there exists an n2 such that n1 plus n2 is equal to 5. Okay? Does that sound good to you? So this is easy. There's infinitely many proofs, but you try it. And assuming you gave it a shot, let me do it my way. Let me try to make it look like a normal mathematical proof. You got to say proof, period. And then you got to just pick values, right? You got to show that this is true. There exists an n1 and an n2 such that n1 plus n2 is 5. Like, there's so many values, right? Let's do a fancy one. Let's be like, let n1 equal -2. That's still an integer, right? And also, n2 equals 7. Then, right, this is very simple, but this is a proof, right? You got to spell it out. Then n1 plus n2, which is -2 plus 7, is equal to 5. And so I've just found 2 good values that this checks out for, and it holds, and it gives me 5. Bam. QED, mic drop. Does that make sense? Like, that's us proving something. Like, you upheld our end of the bargain. We've shown that there's 2 good numbers for which this works. You only have to find the 2, right? We know that there's infinitely many answers, but that doesn't matter. Just pick some good ones, because that's what it means. If there exists means, all right, there's at least one. You can find whichever one is easiest for you to show. Okay, so there's that. All right, here's another one. This is like a counterexample, or the opposite of a there exists. So just tell me, like maybe in English or in writing, show what needs to be proven. State what needs to be proven in order to show that the existential statement below is false. So maybe translate it to math first. There exists a negative integer that is equal to its square. So this is a statement, right? that you could either prove or disprove. We're claiming that it's not true. It's not true, right? That there exists a negative integer that's equal to its square. So give that a try. Figure out what you need to show. Like maybe translate it to math. Like what is the final theorem that you would try and prove to disprove this? Okay? So maybe push that negation inwards is my hint to you. All right, so what is this in math? This is like trying to say that, all right, there exists a negative integer that's equal to its square. Let's call that thing x. There exists, or let's call it I this time. There exists an integer I such that it's negative, right? I is less than 0, and it's equal to its square. And I squared, I squared is equal to I, right? So that's your statement. This is what you're trying, that's what the original statement, and we're trying to show that it's not true. We're trying to disprove it, right? So that's that. We can't really initially prove this. We kind of got to push the negation inward. So let's do that, all right? Then we'll come up with something that we can eventually show. So how do you push the negation inwards? Well, if you push it inside here, you get that for all I, it flips to for all, and then you negate the inside. For all I, it's not true that I is less than 0, and I squared is equal to I. And then you can push that negation inside even further, right? You have a De Morgan's law. You have, all right, let me spell it out for you. It's, all right, there's for all I, well, you have the and of these two sides negated, right? Or sorry, you have the or, excuse me, you have the or of those two sides negated. You have, well, not I less than 0 or not I squared equal to I. See that? That's that one. That's De Morgan's law. And then we can, of course, simplify these two. You know what the opposite of those things are. So for all I, well, what's the negation of I is less than 0? That's greater than or equal to. So I is greater than or equal to 0, and what about this? Or sorry, still an or. I is greater than or equal to 0, or I squared. What's the negation of an equality? It's disequality. I squared is not equal to I. So this is what you would prove. You got rid of all the negations. This is what you would show to disprove that original statement. For all I, either I is greater than or equal to 0, or I squared is not equal to I. Okay, that is apparently a statement that is exactly equivalent to this idea. Which kind of seems different, right? It's not intuitively the same, but we've proven that through our rules, right, that it must be the same thing. So that's kind of nice. All right. So that brings us to like the standard way now of proving probably a for all. All right. Usually you're going to use a direct proof to prove a for all because it's most likely going to have an implication in it, right? So a direct proof is a way to prove that a conditional is true, all right? And usually there's some quantifier at the end of it as well. But you have a conditional at the end of the day. That's what a direct proof shows. That's how you can prove that a conditional statement P implies Q is true, all right? Pretty much every proof you're ever going to write will look like this, all right? It will be a direct proof, all right? And the strategy is to make a direct proof. You assume that the hypothesis is true, assume that you're in the universe where the hypothesis is true, and then show that the conclusion is also true, right? That's how you do a direct proof. That's how you prove that this conditional statement was true, right? And let me prove to you, I guess that's a pun, that this is a valid form of reasoning, that a direct proof really does work, all right? So let me show you the truth table for P implies Q. So these are the variables, true, 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 false, false, true, false, false. These are all the different ways, right? You can have, sorry, that's supposed to be a false. These are all the different combinations of those variables, and then like, what's the truth table look like? It's got true, false, true, true. So what you're doing in a direct proof is showing that your implication is true, that you're in one of these three cases, right? That's what you're trying to show. Does that make sense? And so another way of saying that, you're trying to prove that you're in one of these three good ones. An alternative way of proving the thing is just show that this is not possible, right? Show that you can't get here. Show we can't get here. Because that's the only way that would ruin this, right? Show we can't get here. That's the only way it could be false. Just show that that's impossible. So what you do is like, all right, show that when P is true, right? Because here are the cases where P is true, and this is one of them. These are the only two cases where P is true. Assume that if P is true, then the hypothesis, or sorry, if the hypothesis is true, just show that the conclusion must also be true, because that's what separates this one from this one. Do you see that? Because if you've shown that, assume that P is true, assume your hypothesis is true, show that your conclusion is also true, that's proven that you're only in this case, right? Does that make sense? That's proven that you're not in this one. You can't get to that one. You see that? And then you don't even need to care about, don't even need to worry about if the hypothesis is false, because the conclusion is like, the implication is vacuously true, we say. So you don't even need to worry about that case. You're just like showing that you're not in this row. All right, does that make sense? So you're assuming the hypothesis is true. That's forced you into one of these, and then you're trying to show that the conclusion is also true, because that's going to guarantee you're in the first one and not in the second one. Okay? That's the idea. So that's a direct proof. Let's get a lot of practice with it. All right. So here's an example of a direct proof. Let's prove this statement using a direct proof. If x is an even integer, then -1 to the x power is equal to 1. All right, let me prove that to you using a direct proof. Do you see how there's an implication? It's an if-then, and there is also a for-all. There's usually also going to be a for-all to go along with this most of the time. All right, so this is like, what is this statement in math, first of all? It's trying to say, for all x, if x is even, so I'll just say x even as an abbreviation for that. If x is even, then -1 to the xth power, that's a weird word, is equal to 1. Okay, so you got that. That's the math. And do you see how this is like, this is p, x is an even integer, and this is kind of your q, that's your implication. All right, then we have our p implies q now. So we're going to use a direct proof. We're going to assume that the hypothesis is true, and then we're going to prove that the conclusion must also be true under that assumption. All right, that's all we got to do, and then we've shown the whole thing. We've proven that the if-then checks out, that the statement is true. We've proven this entire for all, right? If we assume that x is arbitrary, right? That's the goal as well. That will give us our generic proof of a for all. So we're kind of like doing that on the side, but it's just so common. It's just like second nature eventually. Okay, so let's go back to this. So proof. So we know what p and q are now. So proof. First of all, we need to get inside here. Like we need to we're doing a generic for all proof. So like let's assume that x is like some generic number. So assume, let's introduce the variable. Assume x is an integer. Like we assume we have an x. So then we just need to show the inside. And then also assume that x is even. We're like doing two assumptions at once. Assume x is an even integer. So we've generated it, and we've also like assumed the left side, even integer. Right? So we have a generic number, a generic x, and we also have that this is true about it. Okay? All right, we have assume x is an even integer, and we're trying to come up with this is true, and we need to show that this is true about it. All right? We need to show that -1 to the x power is equal to 1. All right? So assume x is even. Where do we go? How do we do this? Like, how do we come up with like an equation for this? Like, how does it all work out? So my hint to you is always, if you see like evenness, some adjective that has no math involved, convert it to math. Assume x is an even integer. How do you say that in math? We have this, right? An integer is even if there's an integer k such that x is equal to 2k. All right. So if you know something's even, you can divide it by 2, right? You can pick out that factor. So if you know something's even, so what do we know about x now that we know it's even? We're assuming that it's even. Therefore, x is equal to 2 times k for some k. There exists some k for which this works out. We don't know which one, but it works out for one of them, for some k. And k is also an integer, for some integer k. Okay? See how we get that? Just by knowing that x is even, assuming that it's even. We know that this is true about x. All right? And then we're trying to show this, and watch it work. So now we can do this. -1 to the xth power. Well, what is x? It's 2k for some k. So that's equal to -1 to the 2 times k. Yeah. What's that equal to? You remember how you can use like parentheses around power computations? This is equal to -1 to the 2, square that first, and then take that whole thing to the kth power. Let me make that a bit smaller on the inside. So it's -1 squared. So you can just do that twice, right? That's the same as the left side, to the k. So do this time to the squared first, to the second power, then to the kth power. That's the same as multiplying exponents. Do you see that? And then this inside, what does that simplify it to? See how that's equal to just 1 on the inside, and then we take that to the kth power. And then 1 to the any power is still 1. So that's equal to 1. Boop. So I started with the thing on the left, got the thing on the right with some reasoning. Under my assumptions, I have shown that under this universe, if this is true, this must also be true. I have guaranteed it. QED, mic drop. Isn't that fun? So that's a direct proof. Assume that the hypothesis is true, prove that the conclusion is true. All right, so we got that one. Your turn. So prove this using a direct proof. So the sum of an odd and an even integer is odd. Okay, prove that. Remember what a direct proof is. Assume the hypothesis, prove the conclusion. You're probably going to want to convert this to math. And then also you're going to want to look at this slide, so I'll pause it up here, with the definition of oddness and evenness. Boop. So you can introduce some variables. See that? They'll be separate each time, but like don't say that they're both k, because that like confuses things. It's not this. Doesn't have to be the same k when you have oddness and evenness. But give it a try. Direct proof. Assume the hypothesis, prove the conclusion. Maybe do it. Convert it to math first. Notice that there's a for all or 2 involved. All right. Let's do it together now, assuming you've tried it. So the sum of an odd and an even integer is odd. So I need some names for these integers, and so I want to quantify. So for every integer x, for every integer y, see I have 2 things. These can be my two numbers. So it's supposed to work for any odd and even integers, right? So for all x, for all y, if x is odd, right, that's going to be the first one, and y is even, then their sum, which is x plus y, is odd. You see I've converted that to math. This is another like thing that you'll have to get used to, how to figure that out. Like just give names for these things, and then like it's supposed to be true for any of them, so they should be for all quantified. For any x and y integers, if x is odd and y is even, then their sum must be odd. That's this statement in math, and now I have some names for things. All right, so let's prove it together. Proof. So assume x is odd and y is even. This is a direct proof. Assume that the conclusion, assume that the hypothesis is true, then we'll show that the conclusion must also be true. All right, can't be false. Assume x is odd and y is even. All right, so we got that. And then what do we know about things being odd and even? Right? If you're odd, you're 2k plus 1 for some k. And if you're even, you're 2 times k for some k. It's not the same variable though, right? So I'll prove that to you. Doesn't have to be the same one. So, like if x is odd, what do we know about x? Well, so x is equal to 2k plus 1 for some integer k. For some integer k. Also, because we know that y is even, y is equal to 2 times something else. It does not have to be the same k, first of all right? So this is not right. Let me do this quickly. Y is equal to 2k for some k. This is not true, because like this is implying that like if x is 7, then y must have been 6 or something. That's dumb, right? Can't be the same k. So we're going to use a new variable name. Let's call it m instead. So y is equal to 2 times some integer, and I'll just make a fresh name for that integer. For some integer m. Just like as a side note, just to show this to you in red. Don't use k again. Doesn't work out. So it's got to be a fresh variable name. So all right, there we go. We have that is true. And then what we need to show now, we need to show that x plus y is equal to, or x plus y is odd, right? We have to show that x plus y is odd, which means it's something times 2 plus 1. It's an integer times 2 plus 1. So we need to show that x plus y is equal to, like it's odd, right? Which means it's equal to 2 times an integer, let's call it r this time, plus 1 for some other integer r. Does that make sense? That's what it means for x plus y to be odd. It's the multiple of something times, or it's something times 2, right? It's a multiple of 2 plus 1. There's always remainder 1 there. So that's what's going on. All right, and so now let's start with this side and try and come up with a good value of r. So x plus y, what do we know about it now? X is equal to this, so y is equal to this. Well, let's substitute. That's equal to then 2k plus 1 for the x, and then another 2m for the y. Cool. And that's equal to, we got, all right, 2k plus 2m plus 1. Ooh, do you see what a good value of r could be here? It's starting to look like this, isn't it? I just need to find whatever r could have been, find a value for it. So that I can factor out a 2 from that first bit, right? From here. That's equal to 2 times k plus m plus 1. Cool. I've discovered that x plus y is equal to 2 times an integer plus 1, because 2 integers added together is still an integer. This could be my r value. This must be my r value. You see that? That's my integer that I'll multiply by 2 and add 1 to get x plus y. So that proves beyond a shadow of a doubt that x plus y is odd. Do you see that? Therefore, x plus y is odd. Bam. QED, mic drop. Awesome. All right, I hope that's starting to make a little bit of sense. I hope you got a little bit of that, if not all of it done. Do yell at me if you have any questions about this stuff, because this is what I want you to get very good at. Direct proofs are going to be our life. All right. There's always a conditional to prove. All right. You try this one now. Another one. Following statement using a direct proof. Prove it the same way again. So for any positive real numbers, call them x and y. X plus y is greater than or equal to the square root of x times y. So prove that. Convert it to math. All right, and then what's being quantified over? Got x and y. They're for all quantified over. All right, and then prove this about it. Do you see the direct proof? Where's the implication? You got to notice that as well. All right, so give that a try. All right. Also, real numbers. What that means is decimal numbers, not just integers. Decimals are okay. Decimals are okay. Like you could be, x could have been like pi. It's totally okay, totally fine. That's allowable for real numbers. All right, so what's the math form of this? Well, for any positive real numbers, x and y. So it's talking about x and y. For every x and for every y, we're quantifying over them. Could be any of them. All right, we do that. And then what are we assuming about them? So we got an if-then statement here secretly, because that's what we need for a direct proof. What's the if part? Like this is our conclusion. What's the if part? If they're positive, right? If this is true, then this is true. If they're positive, then that's true about those positive numbers. Okay? That's the idea. So if x and y are positive, so how do you write that in math? If x is greater than 0 and y is greater than 0, then what's true about them this? X plus y, their sum, x plus y greater than or equal to the square root of x times y. Okay? That's what's going on. And that is going to be our proof. So do you see the P and the Q? Do you see what we're quantifying over? What's the strategy? Because we're working our way from left to right when we're proving stuff. We have a for all. And how do we do a for all in general? We have to just like assume an arbitrary element of the domain and like prove the rest for it. Okay? That's the idea. And then for our direct proof, we are assuming the hypothesis, then proving the conclusion. So the game plan is going to be this, and you'll get used to it, I promise, if it's not making enough sense. We need to introduce these variables. We need to assume that we have an arbitrary x and y. Assume, that's the very first part of this proof. Assume that we have an arbitrary x and y because it needs to work for any of them, right? It's a for all. If we have proven something about arbitrary variables, the for all checks out, right? It must work for all of them. Assume arbitrary x and y. Let's see, how do I want to do this? Assume arbitrary x and y. And then, let's make this smaller, I'm sorry. Do it over here. Assume arb x and y. And then, it's a direct proof. So you're assuming this and proving this. So assume this side. Assume this is true. And then we want to prove that this is true. That's the goal. So now let's do it. let me show you my way. So proof. Let me write that a little bit better. Proof. Period, usually. Let's see. Well, we need to introduce some variables. Assume that x and y are arbitrary numbers, and then also assume that x is positive and y is positive. So you can do that in one sentence. You can be like, assume x and y are positive. Do you see how I've introduced them? Assume that they're arbitrary, and I've also assumed that side condition as well. Assume the hypothesis about them in this implication. Assume that they're positive. Assume x and y are positive, real numbers. All right. What I need to do now, what I need to show to complete this proof is that adding them together is greater than or equal to the square root of xy. Okay. That's what I need to show. So what do I know right now? All right. Like x and y are positive. Let's write down all the mathematical facts I know in math. All right. So what do I know right now? I know that x and y are positive. So x is greater than 0 and y is greater than 0. All right. To get rid of a square root, you're probably going to want to squared stuff. So like, what do we know about their squareds as well? If I know x is greater than 0, for example, if I know x is greater than 0, I can square both of these sides. I can multiply both sides by x, right? And that gives me that x squared is greater than 0 times x, which is just 0. See that? 0 times x, which is equal to 0. And I know the same for y. Y squared is also greater than 0. You just multiply both sides by y. That's useful. Also, either of these. Let's take the first one. I can multiply both sides of this by y, and I get that xy is greater than 0 times y, which is also still 0. So x times y is greater than 0. See that? I get that. So x times y is greater than 0. I have that. Okay, cool. Now, all right, it's going to look a little weird. Eventually, I need to get x plus y and square roots of things. So I want to get this like into a place where I can take the square root and have an xy. So I want to end up with like just xy by itself on the right. So you kind of work backwards when you do this. But I kind of want to have this, right? I want in the back of my mind, I want like x plus y squared, and I just want xy. Does that make sense? Like I'm squaring both of those. Because then I could take the square root. So like I want to formulate both of these, because I know nothing about square roots right now. It's easier to prove stuff about squareds. So that's where I'm going with this. All right, so let's come up with x plus y squared right now. How do you get that, first of all? What is x plus y squared? That's, if you expand it, x squared plus xy plus y squared. That's equal. Let's see. How do I want to do this? Dun, dun, dun. Let's start here. All right, this does require some artfulness. It took some head scratching. I had to look at the answer to come up with this. So don't feel bad if this is not coming to you immediately. But the idea is to work your way backwards, all right, from what you know. So all right, this is greater than 0. All right, this is greater than 0. Why? Because because x squared is greater than 0, y squared is greater than 0, and x times y is also greater than 0. So they're all greater than 0 things. You can add them up, still greater than 0. Okay? So that's greater than 0. I can use that, and I can add another xy. X squared plus 2xy plus y squared. So now it's 2 xy's instead of just 1. I add xy to both sides, so it's greater than xy now. That's the trick, right? And now I can factor this side. Therefore, that's equal to x plus y squared. Cool. And then I have that that's greater than x times y. See that? And now I'm home free, because I can take square roots of both sides. So now I have x plus y is greater than the square root of xy. And if it's strictly greater than, it's totally greater than or equal to at the same time. See that? It's just like, we lost information. It's really greater than. So therefore, x plus y is greater than or equal to square root of xy. See how I went from this to this? Like, this is less information. Sure, if it's already greater than, it's totally greater than or equal to as well. And that is what I wanted to show. Under the assumption that x and y are positive, I came up with a bunch of stuff and a bunch of mathematical reasoning. It took a bunch of lines of mathematical reasoning, but we got there. to the end, all right? This is definitely a harder one. You'll have to work your way backwards, just like noticing, okay, I can prove stuff about squareds. Let's end up with that somehow, okay? That's the idea. So, all right, one more. You try this one now. Prove the following statement using a direct proof. The average of two odd numbers is an integer. So this is going to look a whole lot like this one. You could use the same strategy, but you try this. Convert it to math and then prove it. The average of two odd numbers is an integer. All right, so let's convert it to math. So for all x, for all y, let's call those numbers x and y. If they're both odd, if x is odd and y is odd, see how that's the implication, that's the hypothesis. If they're odd, then their average, if they're odd, then their average is an integer. You have to like work a little bit to figure out what the implication really was. If they're both odd, then x plus y over 2, because that's the average, right? X plus y over 2 is an integer. Let me draw that better. Is an integer, is a whole number, okay? So that's what we're proving. See that? So, assume the hypothesis, prove the conclusion. Must also be true. Assume the hypothesis is true. I cannot spell proof and type and speak at the same time. Wow. One of those days. All right, proof. There we go. We have to introduce these variables and also assume the hypothesis. So assume x and y are odd integers. Assume x and y, or another word for assume is let. It's less writing. So let x and y be odd integers. Odd numbers. All right, they're both integers. So what do I know about odd things, right? So back to our little handy dandy table. So if you're odd, this is true about you. You're something times 2 plus 1. So x is equal to 2 times k plus 1. And y is also equal to something else, right? And y is equal to 2 times some other integer, let's call it m, plus 1, right? For some integers, for some ints k and m. Don't know what they are, but that's how they work. These are arbitrary x and y's, where this stuff is true for them, right? They're just odd. We know that about them. And now we need to show that this is an integer, all right? So x plus y over 2, we need to show that that is an integer somehow. Well, let's plug in what we know about x and y now. X plus y is equal to 2k plus 1 plus 2m plus 1. See how things are going to start canceling. 2m plus 1, that's an m, plus 1 over 2. Cool. Let's combine like terms. It's like 2k plus 2m plus 2 over 2. You see how that's working? And you can totally take out a 2 from each of these. Totally fine. That's equal to k plus m plus 1. All right. So that's the answer. And this, we just need to show that this answer is an integer. And it is, right? So k plus m plus 1 is an integer, int, because k and m are both integers. And of course 1 is an integer, are both integers. And then adding 1 makes it still an integer, right? Adding integers to more integers keeps you in integer land. All right? Therefore, x plus y over 2, because we expanded it into that, is an integer. Isn't that fun? Mic drop. QED. Nice. Wasn't that fun? I feel like I could have filled that in better. I don't know why. That bothers me, but it did. There. Okay, so that is the statement. I hope that's making a little bit of sense to you. With enough examples, like, do you kind of get the feel for it? Like and do you see why it works, why it's valid? Oh no, my computer froze. Hopefully you can still hear me right now. But that's pretty fun. Hopefully you kind of bought this as well. Like that's why this is all working. And then we can just start writing English, and that becomes a proof. All right. So before I end this lecture, Sometimes it's easier to do a proof by a contrapositive, because if you have an implication, you can compute the contrapositive, which is equivalent to the original thing, right? Remember that the contrapositive of P implies Q is not Q implies not P, and these are in fact equivalent to one another. So I don't know, equivalent, three arrows, 3 equality signs there. But you got to swap the hypothesis and the conclusion. So it's not the conclusion implies not the hypothesis. Those two things are equivalent. Isn't that fun? And so let's prove that they're equivalent, in fact. You got P, you got Q. Let's see here. And then you got P implies Q. Let's start with those, and I'll prove that this is also true. That it's equivalent, so the columns are the same. So if you just prove the other, you got the other. You prove one, you got the other. So sometimes it's easier to do a direct proof using the contrapositive, because it's still an implication. See that? So true, 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 false, false, true, false, false, true, false, true, true. And then, all right, let's just spell it out. Negation of Q implies negation of P. What's not Q? What's not P? Bam, bam. So not Q is going to be false, true, false, true. False, true, false. Let's try and keep these lined up as best as I can. False, true. And then I got true, true, false. This one negated is false, false, true, true. Cool. And then now I can compute very easily not Q implies not P. And I'll show to you that they are equivalent statements. So what is this? Well, it's only false if it's true implies false, right? Which is this one. That's the only time it's false. The rest of these, false implies false, false implies true, true implies true, those are all true, right? That's an implication. And now, bam, what do you know? These columns are exactly the same. That's a little too thick. Let's fix that. These columns are exactly the same, and so it doesn't matter if you did P implies Q or not Q implies not P. It means the same thing. You could have used either one. They're interchangeable. And this is really helpful for our proofs, right? Because if you could prove this and you know that this is also true. See that? And this is also a direct proof. You could do like assume not Q and prove that not P is true. Sometimes that's easier. And so I'll also show that these are equivalent using our equivalence rules. So P implies Q. Let's start with that. And then we have that's equivalent to not P or Q, right? Remember that? And then, well, that's also equivalent to Q or not P, which is also equivalent to not Q, right? Because double negation, or not P. And you have a negation of a hypothesis ORed with the conclusion. That's equivalent to not Q implies not P. Okay? So they really are the same, no matter how you want to prove it, that they're the same. And so now, like, if you have one, you have the other. They're both equivalent statements. And one might be easier to prove than the other, is the idea. Okay? So we're going to use contrapositive in a direct proof next time. So I'll see you then.